turn in. So to set this up, so I would say,
Do you have phone sequence like this? That little.
Refine.
There.
Using quick and easy methods.
Pretty good, thanks.
So we found that, and here now you don't have to keep lots of digits in the final answer. You have to keep lots of digits in the calculation. So A is minus 0.56 is good enough. We find A equals minus 0.560, right? Here. B is 0.314. C31 is 0.5. And C41 is 0.0599. Everyone? All right. We're done with the computers. So we find that h of t, which is the inverse of s plus 1 over s4 plus 3s cubed plus 2s is equal to a minus point is the inverse of minus 0.560 over s times. Okay, I'll continue here because I don't want to erase the dictionary yet. So I'll continue here. I'm extremely well coordinated. B is 0.314, and that's times C31 was 0.5. And the last one is so h of t is the inverse of this, And using dictionary, it was expanded dictionary, expanded by these entries. Okay, look at this. The constant goes out. What do I have? S minus A over S minus A squared plus B squared. S, instead of replace the plus A with minus A. Okay, you put minus A, you have plus A here. S minus A over S minus A squared plus omega squared. It's this entry. With A equals minus 0.979. You see that?
Mm-hmm.
Everybody? This is this. So this is minus 0.560. Factors out. And I have S plus A. The A is minus 0.0979 over S plus A squared plus omega squared. The omega is 0.785. So that's going to be this entry into the minus A is what? Plus 0.01. And that's cosine of 0.785 t plus second term has factor 0.314. And what do I have here? B, the 0.78 is omega, so that's the omega, the 0.785 is the omega, over S plus A squared, A being minus 0.0979, plus B plus omega squared. That's this entry here. That's why this alternative is very efficient, because you don't have to do any manipulations. You use directly the A and B you got from the dictionary to write the final answer. So that's e to the 0.0979 t sine of the same thing.
How come you don't multiply by 0.785? Is that like a constant?
What do you mean?
Because the one before you just dragged out the constant, which is negative 0.5.
Right, because the 0.785 is part of what I need here. Omega is part of what I need here. That was important to have it in the equation. It's inverted, not with 1 here, with omega here. So whatever is the constant square, you should have that number here.
Oh, okay.
So the 0.785 square should appear here. This is the part that inverts the sign.
Got it.
That's exactly the point of this. In books, you see just number this and then you have to do extra algebra.
Oh.
This is directly dictionary.
I see.
All right. Plus 0.5 over S inverts 0.5. And this inverts 0.0599 e to the minus 3.1958 t. So that's the h of t. And what do I need to finish it up? I need h of t minus 2. So last thing, it's okay, you don't have to rewrite y prime. If you read that equation up there, just writing h of t minus 2. So h of t minus 2, which is what y prime for t greater than or equal to 2 is equal to minus 0.560 e to the 0.0979 that is replaced by t minus 2 cosine, and I'll change the bracket to this type of bracket, 0.785 that is replaced by t minus 2. Wherever I have t, both here and here, I replace by t minus 2. Plus 0.314 e to the 0.0979 t minus 2 times sine of 0.785 t minus 2. again placing the theta dimension. Plus 0.5 plus 0.0599 equal to minus 3.1958, and replace the t by t minus 2. And here we write this equals y prime of t for t greater than 1. That's it. So turn this in, due 1 week from today. Okay. Clear everyone how we do it?
Yep.
Do we have to turn in Excel as well?
You need to turn in a hard copy printout of Excel, yes. Yes, sir.
This is an unstable transfer function
This would have been an unstable system. You're absolutely right. Since I have positive poles, this is blowing up. You can see as time goes to infinity, what happens to the amplitudes? They blow up. Yes, y prime of t will be blowing up. Everybody clear? All right. So now we're going to perhaps have another hour for fun. Any questions before I move to the brand new chapter? Very, very important. It is very important. I don't think we'll have the time to tune on very first controller today, but we'll be tuning definitely Wednesday. We're going to be tuning controllers. Okay? We're entering now. We have seen how we get transfer functions through a methodical approach, the 4-step approach and everything. But that is not very practical, as I've discussed many ways, unless we have a very simple model which is extremely rare. But in practice, we have either the actual equipment that we're going to be tuning the controller for, or we have the model for the 100 state variable distillation column, and we can use it to simulate and get results from simulations that I can fit to a model.
Is it the bread and butter you were talking about? Is this the bread and butter?
We're going now to the way
Fine.
to actually tune a controller in practice. How do you get the GU that you need for controllers in practice? And we have learned about poles and zeros, particularly about poles. And we have understood that the dominant pole controls what we observe in the system. How many poles exactly? Who will tell me exactly how many poles a real system will have? There's one answer that is the correct answer for how many poles a real system has. 3 is not correct.
1?
Go higher.
25.
Go higher. Say it loud. It was joking. Infinity. Because real systems always have some special inhomogeneity. Things vary with respect to space. So if you wanted to have a perfect model for a real system, definitely would have to be partial differential equation. And we're talking about ordinary differential equations here. A partial differential equation can be exactly approximated by infinite ordinary differential equations. So real systems actually have infinite poles if we had perfect models. Because we never have perfect models, so we wouldn't have infinite poles. But if we wanted to have actual absolute accuracy, 100% accuracy, we would have to have a model with infinite poles. Yes, sir.
You're saying it just changes with position as well?
Yeah, things vary with position. And if you have variation with both time and position, automatically have partial differential equation. So our dx dt equals ax plus bu. We have dimension of x infinity. Then But we know that each pole contributes e to the pole t. And if we have a dominant pole and some space between that and the other poles, all the other pole effects are going to disappear so fast that it's going to be like they're almost not there. And for the majority of physical system behaviors, that's the case, that you can get a damn good approximation of a transfer function by just causing a single pole and a time delay. Exceptions are if we have inverse response or if we have observable oscillation. Then you need to go to more than one pole. Okay? But if you have a zero, if you have to model the right-hand side zero, since you must always have more poles than zeros, you must have at least two poles, and therefore you must have at least second order. And of course, for oscillations, you have to have complex conjugate poles, and again, it requires at least two poles. But in most real cases, if you do a step change in your output, will look sigmoidal with this or something like this. And those systems can be approximated well by just a single pole and time. Which brings us to the next topic, which is first order plus time delay, sometimes called dead time. Okay? What would be the transfer function of the first order plus time delay system? Well, if I have only one pole, yes.
Wait, what is that? What's the difference between that and the one before that you showed us? That seems like the same thing.
Yeah, that's what I'm going to.
Okay. never mind.
That we can model something like that if I have behavior, if I have the actual system and I do a step change in U like that, and I get Y responses that look like this or like that, I can very effectively model this and do my tuning with first order plus time. And in practice, over 90% of the systems are typically tuned as first order plus time. Let's say at least 90% in the order. So this is a very important case, and there have been many methods dedicated to how you tune a system that has a transfer function first order plus time delay. I'm going to teach you two specific methods in this class. I know Dr. Crisaro is working on writing text, and I saw once a page with his text, and he had about 7 or 8 different methods for tuning first order plus time delay system. So we're talking about the most common way of tuning a system. And so what would be the transfer function of a first order plus time delay? Well, I will have only one pole, right? And I will have the time delay. To have only one pole, what should be the size of the A matrix? I have only one pole, 1 by 1, right? Okay, so only
The poles at the bottom or the
one pole,
bottom? The bottom, yeah.
so A is 1 by 1, B is 1 by 1, C is 1 by 1. Your exam second problem was 1 by 1. So